Every second you sit still, you are hurtling through space at a speed no aircraft, no rocket, nothing humans have ever built has come close to matching. You just cannot feel it. And that silence, that complete undisturbed calm you feel right now, is not reassuring. It is actually the most unsettling part of this entire story. Tonight, we are going to strip that silence away, layer by layer, and find exactly how fast Earth is really moving through the cosmos. Each layer will be larger and stranger than the last, each one completely invisible to your senses. And by the end, you will finally understand why a journey this terrifying has always felt, to you, like absolutely nothing. Now get yourself comfortable, hit subscribe, we begin. Right now, in this exact moment, you are doing something that feels perfectly ordinary. You are sitting still. The floor beneath you is solid. The room around you is quiet. Nothing is rattling. Nothing is pressing against you. Nothing in any direction hints that the universe is anything other than calm and patient and fixed. And every part of that feeling is wrong. Not slightly wrong. Not wrong in some technical way that only matters to physicists in conference rooms. Wrong in a way that reaches all the way down into the most basic story your senses have ever told you. You have never been still, not once, not for a single heartbeat, not for a fraction of a second in your entire life. Right now, in this quiet room, you are moving at speeds that should feel catastrophic, and the most unsettling part of all is that you will feel nothing, not a tremor, not a whisper, nothing, because that is the extraordinary nature of what is happening to you. And once you understand it, the stillness you are sitting in will never feel quite the same again. The first thing to understand, and this matters more than it might seem at first, is what motion actually is. Because here is the thing most people never realize. Motion is not a fact. Motion is a relationship. When you say something is moving, you are always, whether you are aware of it or not, saying it is moving relative to something else, some chosen reference point, some object, surface, or background that you have decided, consciously or not, to treat as fixed. This is not a philosophical technicality. This is how physics actually works at its most fundamental level. Picture a perfectly sealed train carriage. No windows, no vibration, a completely smooth, perfectly constant ride. You're sitting inside. Now ask yourself honestly, can you tell you are moving? You cannot look out. There are no windows. You cannot feel it, because if the speed is perfectly constant and perfectly straight, your body registers nothing. The coffee in your cup sits level. A pen dropped from your hand falls straight to the floor, exactly as it would in a room that has never moved. The air around you is completely still. From inside that sealed cabin, traveling at constant velocity, there is no experiment you can perform, no measurement, no test, that distinguishes motion from standing still. Galileo understood this in 1632. In his dialogue concerning the two chief world systems, he described it through a thought experiment aboard a moving ship. Go below deck, he said. Watch fish swimming in a bowl of water. Watch drops falling from a bottle. Watch a butterfly drift from one side of the cabin to the other. Everything behaves exactly as it would if the ship were docked in harbour. No internal observation can reveal that the ship is underway, not if that motion is smooth and straight. What your body can detect is change, acceleration, the moment when speed or direction shifts, the force pressing you into your seat during takeoff, the sudden lurch of turbulence, the deceleration pressing you forward when brakes engage on landing. Those sensations are real because acceleration is real. It involves a genuine force acting on your body. But the 900 kilometers per hour, roughly 560 miles per hour, of smooth cruising in between, that leaves no physical mark on anyone sitting inside it. None at all. Speed itself, pure, uninterrupted, constant speed, is completely silent. And this is where the story stops being abstract. Earth is moving right now, continuously, and not slowly. Let's talk about rotation first, because rotation is where the illusion begins. Earth completes one full spin, approximately every 23 hours, 56 minutes, and 4 seconds. Scientists call this the sidereal day, the time it takes the planet to rotate once relative to the distant background stars. The 24-hour day we use in ordinary life is slightly longer, because Earth is also traveling around the Sun at the same time. To bring the Sun back to the same position in the sky, Earth needs to rotate just a fraction further than one full turn. But the actual spin of the planet, measured against the stars, takes 23 hours and 56 minutes. Now, here is where that number becomes something you can feel in your chest. Earth's equatorial circumference, the distance around the widest part of the planet at its middle, is approximately 40,075 kilometres, or roughly 24,900 miles. That is the total distance the surface at the equator must travel during each complete rotation. Divide that distance by the 23 hours and 56 minutes it takes to complete it, and you get the speed of the surface. At the equator, that speed is approximately 1,674 kilometers per hour, or just over 1,040 miles per hour. Let that settle for a moment before we go further. The speed of sound, the rate at which sound waves travel through air at sea level under standard conditions, is approximately 1,225 kilometers per hour, or about 761 miles per hour. A typical commercial passenger jet cruises at roughly 900 kilometers per hour, or around 560 miles per hour. The equatorial surface of Earth, the ground beneath the feet of everyone living near the tropics, is moving faster than both of them, faster than commercial aviation, faster than the speed of sound itself. No sonic boom, no wind against your skin, no force pressing your body into anything, just silence. But 1,674 kilometers per hour of it, faster than any passenger jet ever built, faster than sound, faster than anything a human being has ever sat inside, and not for a moment, every second, every breath, every day of your life, always. But that speed is not the same everywhere on the surface, and this is where the geometry becomes quietly remarkable. As you move away from the equator toward either pole, each circle of latitude grows smaller. The planet completes one full rotation in exactly the same time everywhere, but the surface at higher latitudes has a shorter path to travel, so it moves more slowly. At around 45 degrees of latitude, a line running through parts of France, the northern United States, and Central Asia, the rotational speed drops to approximately 1,184 kilometers per hour, or about 736 miles per hour. Still faster than a commercial jet, still supersonic by most conventional measures, but meaningfully slower than the equator. At the poles, the geometry changes almost completely. Stand precisely at the North Pole or the South Pole, and you are not sweeping through space in a great arc. You are simply turning slowly in place, like a key rotating in a lock. The distance you travel during one full rotation of Earth approaches almost nothing, but the planet is still spinning. You are still rotating with it. The motion never stops. It only becomes smaller. And now comes the question that most people form at exactly this point. If the surface near the equator is moving at over 1,000 miles per hour, why isn't the atmosphere being stripped away? Why aren't the oceans sloshing sideways? Why isn't everything on the surface being flung outward? The answer is that everything is spinning together. The atmosphere did not arrive after Earth was already rotating. It formed alongside the planet, born into the same rotation from the very beginning. The air inside the room where you are sitting right now is rotating at the same speed as the floor beneath you, the building around you, and the ground beneath that. There is no stationary layer of air nearby for the rotating surface to rush against. A hurricane requires a difference in speed between neighbouring bodies of air. Earth's rotation, shared uniformly by the atmosphere from the ocean floor to the upper stratosphere, does not produce that difference at the surface. Everything moves together. There are, however, measurable consequences, small ones, but real. Earth's rotation does produce a tiny outward force, what physicists working in the rotating reference frame call centripetal acceleration, the effect most people know informally as centrifugal force. At the equator, where rotation is fastest, this outward push measures approximately 0.034 meters per second squared. Earth's gravitational pull at the surface measures approximately 9.8 meters per second squared. The rotational effect amounts to less than half of 1% of gravity. No human body can feel it. No ordinary scale registers it without extraordinary precision. But over 4.5 billion years, that tiny force left its mark on the shape of the planet itself. Earth is not a perfect sphere. The equatorial radius, the distance from Earth's centre to the surface at the middle, is approximately 21 kilometres, or 13 miles, larger than the polar radius. That permanent outward bulge is the imprint of billions of years of rotation, pressed into the body of the planet, like a thumb held against wet clay. Weigh yourself precisely at the equator, and then again at the poles, and a sensitive enough instrument would show a small, real difference. You would weigh very slightly less at the equator, the combined result of the outward rotational effect and the slightly greater distance from Earth's gravitational center. The rotation leaves no sensation in your body, but it leaves evidence everywhere. The most powerful piece of that evidence arrived in a single afternoon in Paris in 1851. The French physicist Léon Foucault had spent years searching for a way to make Earth's invisible rotation visible, something a person could watch with their own eyes in a single room. The invitation he sent to colleagues contained one sentence: "You are invited to come and see the Earth turn." In March of that year, at the Pantheon in Paris, Foucault suspended a brass-coated lead ball weighing 28 kilograms, roughly 62 pounds, from a steel wire 67 meters long, about 220 feet, attached to the interior dome far above the crowd. He set it swinging in a slow, careful arc. The people gathered in that hall watched it move, back and forth, and then, slowly, impossibly, the plane in which the pendulum swung began to rotate, not because anyone had touched it, not because the pendulum itself had changed direction, because the floor of the Pantheon was turning beneath it. The pendulum, once set in motion, continued swinging in a fixed direction relative to the distant stars. Earth rotated beneath it, and every person standing in that hall could see, with nothing more than their own eyes, that the ground they were standing on was in motion. The crowd had come expecting a demonstration. What they witnessed was proof. That single pendulum settled something that centuries of argument and astronomical calculation had never quite managed to make felt. Earth rotates. You are rotating. You have always been rotating. Your body has never once sat still, not for a single second, not in your entire life. And yet the stillness felt complete. It was convincing. It was total. The deception is perfect, because everything moves together. And here is what makes that so deeply strange. The evidence has been there the whole time, in the slight flattening of the poles, in the weight you lose imperceptibly at the equator, in the slow rotation of every pendulum left to swing freely on the surface of this planet. The motion was never hidden, only the sensation was missing, and without sensation the human mind does not look for what it cannot feel. But here is the thing that rotation, this supersonic, continent-spanning, pole-flattening, pendulum-deflecting spin, cannot prepare you for. Rotation is only the first layer of Earth's motion, the smallest one. the nearest one, the one that, in the full picture of what this planet is actually doing, barely registers, because wrapped around it, in the vast and silent darkness beyond the atmosphere, Earth is moving in an entirely different direction, not spinning in place, but hurtling outward along an enormous curving arc through space. And the speed of that journey makes 1,674 kilometers per hour feel like standing still on a quiet street, the number waiting just beneath everything you have learned in the last few minutes is one that most people have never been told. And once you hear it, the silence around you will carry a different weight entirely. That number is this. Every single second, Earth moves approximately 29.8 kilometers through space along its orbital path around the Sun. Not 29 kilometers per minute, not per hour, per second. Convert that into the units we use for speed on the ground, and it becomes approximately 107,200 kilometers per hour, or roughly 66,600 miles per hour. Earth has been moving at this speed, without pause, without slowdown, without deviation, for 4.5 billion years, and no one on board has ever felt it. Before that speed can land the way it deserves, there is something more fundamental to understand, something that most people have never had explained to them clearly, and without which the number means little. Earth is not cruising through space along some stable, self-propelled path. Earth is falling, right now, continuously, toward the Sun, and the only reason it has not arrived in 4.5 billion years is that it is also moving sideways, fast enough and precisely enough that by the time it has fallen a small distance toward the Sun, the curve of its path carries it forward, past the point of closest approach. The Sun recedes beneath it, and so it falls again, and misses again, and the arc continues year after year, without engine, without steering, without anything to maintain it except momentum and gravity in permanent, perfect tension. This is what an orbit is, not a fixed track with walls that hold the planet in place. An orbit is a continuous free fall in which the sideways speed is so precisely matched to the gravitational pull that the falling object perpetually misses what it is falling toward. Isaac Newton grasped this with striking clarity in the 17th century. Imagine, he proposed, a cannon positioned at the top of a mountain so tall it rises above the atmosphere. Fire a cannonball horizontally, too slowly, and it arcs toward the ground nearby. Faster, and it travels farther before the curve of its fall brings it down. But at exactly the right speed, the surface of the Earth curves away beneath the cannonball as fast as the cannonball falls toward it. The ground never arrives. The ball circles the planet. It is in orbit. Earth does the same thing around the Sun. Vastly larger, vastly faster, but the same physics. The Sun is simply too far below Earth's path to ever catch it, and the sideways speed is simply too great to ever let it escape outward into the dark. The average distance between Earth and the Sun, what astronomers call one astronomical unit, their standard unit of measurement within the solar system, is approximately 149,600,000 kilometers, or about 93 million miles. The full circumference of Earth's orbital path around that distance covers roughly 940 million kilometers, about 584 million miles, every single year. That is the distance our planet travels in the time it takes Earth to circle the Sun once. The distance from here to the Sun and back, looped into a single journey repeated without interruption. Let's put 107,000 kilometers per hour into a form the body can actually feel. In 1 hour, Earth's orbital motion would carry you around the entire equatorial circumference of the planet, more than 2.5 times. Not around a city, around the whole Earth, twice, with distance left over. In the time between one heartbeat and the next, roughly 0.8 of a second at a resting pace, Earth has moved approximately 24 kilometers through its solar orbit. That is the distance from the centre of London to Heathrow Airport, from downtown Chicago to O'Hare. Every heartbeat, right now, while you read this sentence, without pause, without exception, without end. Now place that against what human engineering has managed to build. The SR-71 Blackbird, the fastest air-breathing jet aircraft ever officially flown, which set its absolute world speed record in July 1976, reached a peak speed of 3,529 kilometres per hour, or 2,193 miles per hour. That record is certified by the Fédération Aéronautique Internationale. It has never been broken. Earth moves approximately 30 times faster than that. The Apollo 10 spacecraft, which set the record for the highest speed ever achieved by a crewed vehicle on May 26, 1969, during its return from the Moon, reached 39,897 kilometers per hour, or 24,791 miles per hour. That record also stands, more than 50 years later, as the fastest any human being has ever travelled. Earth's orbital speed is nearly 3 times faster than that. No vehicle assembled by human hands, no aircraft, no spacecraft, no object ever built and accelerated, moves at even a fraction of the speed at which the planet carrying it has travelled every day of its existence. The fastest we have ever gone is less than a third of the speed we are already moving at right now, without effort, without fuel, without even knowing it. Here is something that should feel deeply wrong, and yet is one of the most elegant truths in orbital mechanics. Earth's mass, the total amount of matter in the planet, is staggering. Approximately 6 septillion kilograms, a number so vast it requires scientific notation just to write, and yet that mass has absolutely no effect on how fast Earth orbits the Sun. None. The reason goes back to Galileo. In the late 16th century, through careful experiment, he demonstrated that objects of different masses fall at exactly the same rate under gravity. A feather and a lead ball, dropped from the same height in the absence of air resistance, hit the ground at exactly the same time. Mass does not change the speed of a fall. It only changes the force required to produce it. Since an orbit is a form of fall, mass does not determine orbital speed. Distance from the central body does. A grain of dust positioned at Earth's exact distance from the Sun would orbit at precisely the same speed as Earth, 107,000 kilometers per hour, 66,600 miles per hour. The 6 septillion kilograms are, in this sense, irrelevant. But the orbit is not a perfect circle. Earth's path around the Sun is very slightly elliptical, like a circle that has been gently pressed from 2 sides, stretched just barely out of round. The eccentricity is small, only about 0.017, but it produces a measurable consequence. At the closest point of the orbit, called perihelion, Earth sits approximately 147 million kilometers, or 91 million miles from the Sun. At the farthest point, called aphelion, that distance grows to about 152 million kilometers, or 94.5 million miles, a difference of roughly 5 million kilometers, about 3 million miles, between the planet's nearest and farthest approach. That small difference changes the speed. The pattern, faster when close, slower when far, was first described with mathematical precision by the German astronomer Johannes Kepler in the early 17th century, working from the meticulous observational data left behind by the Danish astronomer Tycho Brahe. Kepler's second law states that a line drawn from the Sun to Earth sweeps equal areas of space in equal amounts of time. Closer in, Earth sweeps a short, wide triangle in any given interval. Farther out, it sweeps a long, thin one, covering the same total area with a wider arc. To do this at a consistent rate, the speed must change. Perihelion, Earth's closest approach, falls in early January, around the 3rd or 4th of the month. Most people in the Northern Hemisphere find this counterintuitive. January is winter. The Sun feels distant. Yet that is precisely when Earth moves fastest in its orbit, at approximately 30.3 kilometres per second, or about 109,000 kilometres per hour, which is roughly 68,000 miles per hour. Aphelion, the farthest point, falls in early July, around the 4th of the month, northern summer. Earth at its most distant, moving at its slowest, approximately 29.3 kilometres per second, or about 105,000 kilometres per hour, which is roughly 65,000 miles per hour. The difference between January's speed and July's speed is roughly 1 kilometre per second, about 3,600 kilometres per hour, or about 2,200 miles per hour. Enormous by human standards, but spread across months. Too gradual, too smooth, too shared among everything on Earth's surface for any body to register it as a force. The sealed cabin remains sealed. The reason this orbital speed leaves no trace on the body experiencing it runs deeper than simple familiarity. It is not merely that the speed is constant, it is that the speed is shared entirely equally by every object and molecule that has formed in the Earth's vicinity since the solar system was young. The atmosphere formed from the same rotating, orbiting cloud of material as the planet beneath it. It was not deposited onto a moving Earth from some stationary position in space. It condensed and accreted as part of a moving system. Every molecule of air above your head carries the same orbital momentum as the ground beneath your feet. Every ocean, every cloud, every atom of the surface and the sky has been moving at this speed for billions of years. Nothing resists it. Nothing is left behind. And so nothing creates a force for the body to detect. There is a thought experiment that makes this almost physically vertiginous. If you were to jump, push off the floor and rise half a metre into the air, what would happen to your orbital velocity? Your instinct might be that losing contact with Earth means losing Earth's motion, that the planet would race forward beneath you, leaving you behind. But it would not. Your body carries Earth's orbital momentum with it the moment it leaves the ground. Your jump adds perhaps 2 or 3 meters per second to your vertical motion. Earth's orbital speed is 29,780 meters per second. Your jump changes your total speed relative to the Sun by less than 1/100th of 1%. When gravity brings you back down, you do not land on a planet that moved without you. You return to the surface as a participant in the same orbit, your position relative to Earth essentially unchanged. This is conservation of momentum, the principle that a moving object retains its momentum unless a force acts to change it. Your body carries Earth's orbital motion the way a passenger carries the speed of the train they just stepped off of. For the brief moment, they are airborne. They are still moving at the train's speed. That same principle is what makes every space mission in human history possible. No rocket ever launched from Earth began its journey from zero. Every mission, from Sputnik to the Voyagers to the most recent Mars lander, began with Earth's 107,000 kilometers per hour of orbital speed already built in. That momentum is a free gift from the planet. It costs nothing. Engineers do not need to generate it, they inherit it. A mission to Mars does not need to overcome Earth's motion or fight the Sun's gravity from scratch. It needs only to change Earth's orbital speed by a small amount, add enough velocity to swing the spacecraft from Earth's orbit onto an elongated elliptical path that intersects Mars's orbit roughly 7 to 9 months later. The Sun's gravity does most of the work, curving the trajectory inward as the spacecraft coasts across the gap. The whole operation is less about raw power and more about timing, launching at precisely the moment when Earth and Mars are aligned so that the transfer path connects them. The journey to Mars is not an escape from cosmic motion. It is a careful, calculated change between 2 different solar orbits. And here is the paradox at the center of all of this. Earth has been falling toward the Sun for 4.5 billion years. Not metaphorically, physically, continuously, actually falling. pulled by gravity at every instant, accelerating toward a star 149 million kilometers away for 4.5 billion years, and it has never arrived because it keeps moving sideways, precisely, continuously, at exactly the right speed. The falling and the forward motion are matched so exactly that Earth traces the same enormous ellipse year after year, the sun's gravity bending its path inward just enough to keep it from flying out into the void, but never enough to draw it in. No engine maintains this. Nothing replenishes it. The orbit is entirely self-sustaining, set in motion when the solar system formed, and preserved by nothing more than the momentum of creation continuing through empty space. Think about that for a moment. The stability of every living thing on this planet, every season, every tide, every predictable sunrise, rests on a fall that has been perfectly timed for longer than the Earth itself has existed. Before we leave this orbit, there is one common misconception worth addressing carefully. Because the Sun is also moving through the galaxy, Earth does not trace a simple flat ellipse through the absolute space of the universe. Relative to the galaxy, Earth's path is something like a helix, a slow corkscrew threading through space as the Sun carries the entire solar system forward. Popular illustrations sometimes show the planets streaming behind the Sun like smoke trails behind a moving chimney, each one a comet-like arc of motion. That image is misleading. The planets do not trail behind the Sun. They move with it, the whole solar system traveling through galactic space as a single formation, the planets maintaining their orbits around the Sun as that Sun carries them all forward together. The correct image is not a comet. The correct image is a spinning disk moving through open air. The disk keeps spinning, the planets keep orbiting, and the whole structure drifts, or rather races, through the Milky Way as one unit, which raises an unavoidable question. If the entire solar system is moving as a unit, how fast is the Sun itself traveling, and what is pulling it? That answer makes 66,600 miles per hour look almost modest. Faster. That is the only honest word for what comes next. The entire solar system, the Sun, all 8 planets, every moon, every comet, every asteroid, every particle of dust drifting through interplanetary space is moving through the Milky Way as a single unit, not drifting, not coasting slowly on some ancient momentum, racing with a violence of speed that makes Earth's 66,600 mile per hour solar orbit look unhurried, and we are completely, perfectly unaware of it. To understand the scale of what the Sun is doing, it helps to first understand where it sits in the structure of the galaxy. The Milky Way is a disk of stars, gas, and dust, roughly 100,000 light-years across. And 1 light-year, to be clear, is the distance light covers in a full year, travelling at 300,000 kilometres per second. A single light-year is nearly 10 trillion kilometres, about 6 trillion miles. The Milky Way spans 100,000 of them. The Sun does not sit at the centre of this disk. Far from it. Our solar system lies roughly 26,000 light-years from the galaxy's core, sitting out in one of the spiral arms, about halfway between the crowded centre and the outer edge. Think of the Milky Way as a vast city, blazing with light at its centre. We live in a quiet suburb, far from the downtown core, watching the glow from a safe distance. At the very centre of that glow sits something extraordinary. The object astronomers call Sagittarius A star is a supermassive black hole, a gravitational void with a mass approximately 4 million times greater than the mass of our entire Sun. The observations that confirmed it came from tracking individual stars near the galactic centre over years and decades. Andrea Ghez at the University of California, Los Angeles, and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics led separate teams that mapped these stellar orbits with extraordinary precision, both eventually sharing the Nobel Prize in Physics in 2020 for this work. What those orbits revealed, the only thing that could curve their paths so tightly, was a dark mass 4 million times heavier than our Sun, concentrated into an area smaller than our solar system. But here is what most people misunderstand about our galactic orbit. Sagittarius A star, for all its astonishing mass, does not control our orbit alone. The Sun's path around the galaxy is shaped by the gravitational pull of everything inside that orbit. Every star, every cloud of gas, every concentration of dark matter distributed throughout the galactic disk and halo. The total mass inside the Sun's orbital radius is estimated at roughly 90 billion solar masses. Sagittarius A star, with its 4 million, represents less than a fraction of 1% of that gravitational budget. We are not orbiting the black hole, we are orbiting an entire galaxy, and the speed of that orbit is staggering. The Sun travels through the galaxy at approximately 230 kilometers per second. Convert that into the language of everyday speed, the units on a road sign, the numbers on a weather report, and it becomes approximately 828,000 kilometers per hour, or roughly 514,000 miles per hour, roughly 500,000 miles per hour. Let that settle. In 1 hour, the Sun's galactic motion carries the entire solar system, every planet, every moon, every living thing, a distance of 828,000 kilometers. The average distance from Earth to the Moon is about 384,000 kilometers. In less than 30 minutes, our galactic speed carries us farther than the entire Earth-Moon distance. And this happens not once, not occasionally, but every single minute of every single day, in complete and total silence. Compare this to everything we have already established. Earth's rotation at the equator, 1,674 kilometers per hour. Earth's solar orbit, 107,000 kilometers per hour. The galactic speed of the solar system, 828,000 kilometers per hour. Each layer of motion is not just faster than the last, it dwarfs it. The equatorial rotation, 1,674 kilometers per hour. The solar orbit, 107,000 kilometers per hour. The galactic journey, 828,000 kilometers per hour. Each faster than the last, each invisible, each carried by everything around us, shared so completely that no instrument attached to a human body can detect any of it. Before we go further, there is a question worth sitting with for a moment. Guess how long it takes the Sun to complete one full orbit around the center of the galaxy? Whatever number comes to mind, hold it. The actual answer is almost certainly larger than anything you first considered. One complete galactic orbit takes the Sun approximately 225 million years. Not 225,000, not 225 million centuries, 225 million Earth years. The time it takes for our star to complete one single loop of the Milky Way. Astronomers call this a galactic year. To place that number inside biological history, 225 million years ago, the first small dinosaurs had only just begun appearing on the land surface of a planet still shaped as one enormous supercontinent, a single landmass we call Pangaea. The galactic year that is just now ending, the circuit the Sun is completing approximately now in the modern era, began before the first dinosaur walked, before Pangaea broke apart into the continents we now know, before any creature resembling a bird or mammal had ever evolved. That is one galactic year, and the Sun has completed approximately 20 of them since it formed. 20 galactic circuits. In each one, the entire story of Earth's living history could have unfolded from scratch. 4.5 billion years of geological upheaval, extinction events, continental drift, and biological evolution. All of it fits neatly inside 20 laps around the galaxy. The orbit itself is neither perfectly circular nor completely stable. As the Sun moves around the galactic center, It also bobs gently up and down through the flat plane of the galactic disk, the densest region of stars, gas and dust at the midline of the Milky Way. The Sun oscillates through this plane roughly every 60 to 70 million years, crossing through the densest region approximately every 30 million years. Think of it like a spinning coin wobbling as it rolls along a table, dipping slowly above and below the surface on a cycle far too long for any human concept of time to grasp intuitively. But there is a further complication. The galactic orbit is also not perfectly smooth because not all matter in the galaxy is distributed uniformly. The spiral arms, those sweeping concentrations of stars, gas and dust that give the Milky Way its characteristic structure, represent regions of higher density that the Sun passes through over timescales of many millions of years. And here is something rarely mentioned. Every star in the sky is also moving through the galaxy on its own path, at its own speed, in its own slightly different direction. No two stars orbit identically. To describe this properly, astronomers use the concept of the local standard of rest. This is the average velocity of stars in the Sun's general neighborhood, used as a baseline, a kind of cosmic reference point for measuring individual stellar motions. The Sun does not sit exactly on this baseline. The Sun has what astronomers call a peculiar velocity, a slight additional motion, about 20 kilometers per second, in a specific direction relative to neighboring stars. That is roughly 72,000 kilometers per hour, about 45,000 miles per hour, of drift relative to the local stellar neighborhood, on top of the shared galactic orbital speed. Each nearby star has its own peculiar velocity. Each drifts on a slightly different path. The galaxy is not a rigid structure with stars locked into fixed positions. It is a vast, churning collection of billions of individual objects, each tracing its own slightly different orbit, the whole arrangement held together by gravity but continuously shifting in its fine detail. This motion produces real acceleration. The Sun follows a curved path around the galaxy, and any curved path requires a continuous change in direction, which means a continuous acceleration, even at constant speed. Physicists can calculate this galactic centripetal acceleration, the gentle, constant tug that keeps the Sun from flying out of the galaxy entirely. The number they find is extraordinarily small. The Sun's galactic acceleration is roughly 50 billion times weaker than Earth's surface gravitational pull. To put that in terms of physical sensation, Earth's gravity is what keeps you in your chair. The galactic acceleration affecting the entire solar system is so vanishingly weak that it would not move a single atom of dust sitting on a perfectly frictionless surface over the course of a human lifetime. It is real. It is measurable with sufficiently precise instruments, but the human body does not register it, and it never will. And yet this galactic motion, specifically the oscillation through the galactic plane, has produced one of the more provocative and genuinely unresolved questions in modern science. Some researchers have noted that the timing of several major mass extinction events in Earth's history appears to correlate loosely with the timing of the solar system's periodic crossings through the galactic midplane. The proposed mechanism involves the galactic disk's higher density disturbing the Oort cloud, the vast, distant swarm of comets at the outer edge of the solar system, sending showers of icy bodies toward the inner planets more frequently during plane crossings. Papers on both sides of this question exist in the scientific literature. Some analyses find a statistically suggestive pattern. Others argue, equally forcefully, that the correlations are too weak, too dependent on which extinction events are selected, and too sensitive to the exact timescale used to be considered reliable. Several independent studies have found no statistically robust signal at all. The honest answer, as of current scientific understanding, is that the proposed connection between galactic plane crossings and mass extinctions on Earth remains disputed and has not been established to the satisfaction of the broader scientific community. The pattern is intriguing enough to study. It is not established enough to treat as settled. What it does illustrate, however, is something more profound. The idea that our position in the galaxy, the specific arc of the Sun's orbit, the oscillations above and below the galactic plane, may not be entirely irrelevant to the history of life on this planet. The galaxy is not merely a backdrop. It is in some ways an environment we are moving through. Our understanding of all of this has been transformed in recent years by a single extraordinary instrument. ESA's Gaia spacecraft, launched in December 2013, has been systematically mapping the positions, distances and motions of over 1 billion stars across the Milky Way. It does this by measuring two distinct components of stellar motion. The first is proper motion, the slow drift of a star's apparent position across the sky, perpendicular to our line of sight as the star moves through space. The second is radial velocity, the speed at which a star is moving directly toward us or away from us, measured through the Doppler shift in its light. A star approaching us compresses its light waves, pushing the spectrum toward the blue end. A star receding stretches them toward the red. Together, these two measurements give scientists the full three-dimensional velocity of each star, its complete trajectory through galactic space. What Gaia revealed, data release by data release, is a galaxy far more complex and dynamic than any previous survey had shown. Streams of stars from ancient mergers, clusters of stellar populations with shared histories, and individual objects whose trajectories had been quietly mapped for the first time. A picture of the Milky Way not as a stable, static structure, but as something living and shifting over billions of years. Among the consequences of this kind of precision mapping is something that might initially seem counterintuitive. Our nearest stellar neighbour, Proxima Centauri, is not a fixed target. Proxima Centauri sits approximately 4.24 light-years from our Sun, the closest known star in the universe. But it is moving. Hubble Space Telescope observations show Proxima drifting across the sky at nearly 4 arcseconds per year, a tiny angle by everyday standards, but one of the fastest apparent stellar motions observed because Proxima is so close. Over the timescales required for any conceivable interstellar mission, Proxima's position would shift substantially from where it appears today. Any spacecraft launched toward Proxima's current location without accounting for its ongoing motion would arrive at an empty region of space. A destination 4.24 light-years away is not a dot on a map. It is a moving object, drifting through the galaxy on its own separate path. To reach it, you must aim not at where it is, but at where it will be. And here is where everything built so far reaches its most unsettling implication. The galactic year takes 225 million Earth years. The Sun has completed approximately 20 of them, 500,000 miles per hour of speed in a direction completely perpendicular to the solar orbit, added silently and invisibly to every other motion we carry. And yet we have not yet reached the outermost layer, because the Milky Way itself, all of it, the entire galaxy, 200 to 400 billion stars, the spiral arms, the central black hole, the dark matter halo, the 100,000 light-year disk of everything we have ever called our cosmic home, is also moving, not rotating in place, not sitting still while the universe expands around it, moving, racing through intergalactic space at a speed that makes the galactic orbital speed of the Sun look, once again, almost modest. The question of what it is moving toward, and what frame of reference can even be used to measure that motion, is the next door in this story, and it is one of the strangest, most counterintuitive, and most deeply revealing things that modern cosmology has uncovered. The answer to that question requires going back further than any distance we have covered, not outward in space, but backward in time, all the way to a moment when the universe was so young, so dense and so hot that light itself could not travel freely, and what that ancient light, finally freed, is still quietly telling us today about our own motion through the cosmos, is one of the most extraordinary measurements in the history of science. When the universe was approximately 380,000 years old, a number that sounds large until you remember the universe is now roughly 13.8 billion years old, something changed everything. For those first 380,000 years, the universe had been a dense, opaque sea of charged particles and energy, all locked together in constant collision. Light could not escape it. Photons were trapped, absorbed, re-emitted, trapped again. The universe was sealed behind its own heat, dark to any observer that might have existed to look. Then the universe cooled just enough, to approximately 3000 Kelvin, a temperature comparable to the surface of a dim red star, for electrons and protons to combine into neutral hydrogen atoms for the first time. The fog cleared, instantly on cosmic timescales. Photons that had been imprisoned for 380,000 years were suddenly free to travel in every direction across the entire observable universe. Those photons are still traveling. Right now, they fill all of space, arriving at every surface, every telescope, every antenna from every direction simultaneously. In the billions of years since their release, the expansion of the universe has continuously stretched them, cooling them from those original 3000 Kelvin all the way down to approximately 2.725 Kelvin. That is 2.725 degrees above absolute zero, the absolute coldest temperature that the laws of physics permit to exist, colder than anywhere in our solar system, colder than the surface of Pluto at midnight. The universe is extraordinarily cold now, and this ancient light carries that cold with it, arriving silently from every direction. We call this ancient light the cosmic microwave background. Microwave because the stretching of space has shifted the photons into the microwave range of the spectrum, the same band of radiation used inside a kitchen microwave oven, though at intensities so faint that detecting them requires instruments of remarkable sensitivity. The discovery of this light happened by accident, and the accident is worth pausing over. In the spring of 1965, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were dealing with a problem they could not explain. Arno Penzias and Robert Wilson had been using a large horn antenna, originally built for communications work with early satellites, to map radio signals from space. But wherever they pointed the instrument, in every direction, at every hour of the day, there was a persistent background hiss, a soft, uniform microwave signal that refused to go away. They checked their equipment. They recalibrated. They found a pair of pigeons nesting inside the horn and removed them, cleaning away what they diplomatically described as white dielectric material. The signal remained, steady, uniform, coming from everywhere at once. A conversation with Robert Dick's team at Princeton revealed that this was not noise. Dick's group had been actively searching for precisely this kind of radiation, the predicted thermal remnant of the early universe. Penzias and Wilson had found it while trying to eliminate it. The hiss they had been treating as an instrument problem was the oldest light in the observable universe, arriving from the moment the cosmos first became transparent. They received the Nobel Prize in Physics in 1978. The cosmic microwave background is, to an extraordinary degree, uniform. Across the entire sky, the ancient light arrives at almost exactly the same temperature, 2.725 Kelvin in every direction. The tiny fluctuations that do exist, variations of roughly 100,000ths of a degree, corresponding to the seeds of all the galaxy clusters and cosmic structure that formed later, are almost impossibly faint. But the largest departure from perfect uniformity is not those tiny ripples of structure. The largest departure is something simpler, and something that immediately tells us about our own motion. One entire hemisphere of the CMB sky appears very slightly warmer than average. The directly opposite hemisphere appears very slightly cooler. The temperature difference between the warmest direction and the coolest is approximately 3.3 thousandths of a Kelvin, 3.3 millikelvin, a number so small it barely seems worth measuring, and yet it contains a precise, unambiguous record of how fast our solar system is moving and in which direction. This is the Doppler effect, applied not to a passing ambulance or a moving train, but to the entire ancient light field of the universe. When an observer moves through a radiation field, the waves arriving from the direction of travel are slightly compressed. Shorter wavelengths, higher energy, fractionally warmer. The waves arriving from behind are stretched. Longer wavelengths, lower energy, fractionally cooler. By measuring precisely how much warmer one direction of the CMB sky is compared to the opposite direction, and using the known temperature of the background, scientists can calculate the exact speed and direction of the solar system's motion through this ancient light. The solar system is moving through the CMB frame at 369 kilometers per second, not per hour, per second. 369 kilometers every second. In 1 hour, that becomes 1,328,000 kilometers, more than 3.5 times the entire distance from Earth to the Moon, every single hour, or expressed in miles, approximately 825,000 miles per hour. 825,000 miles per hour, 8 times faster than Earth's solar orbit, 30 times faster than the Sun's galactic speed within the Milky Way, more than 20 times faster than the fastest spacecraft ever launched from Earth. But this is only the solar system's speed. When scientists carefully account for the solar system's orbital motion within the Milky Way and the Milky Way's motion within our local cluster of galaxies, a group of roughly 50 galaxies we call the local group, dominated by the Milky Way and the Andromeda galaxy, they can isolate the bulk motion of the entire local group through the CMB frame. The local group as a whole moves at approximately 620 kilometers per second relative to the ancient background light. In hourly terms, 2,232,000 kilometers per hour, nearly 6 times the Earth-Moon distance every hour. In miles, approximately 1.387 million miles per hour, over 1.3 million miles per hour. Not the solar system alone, the entire local group of galaxies, streaming through space, pulled by the gravitational influence of enormous structures tens and hundreds of millions of light years away. And here is where this question becomes genuinely strange. We cannot add these velocities the way we add numbers. Earth's rotation points outward from the equatorial plane. Its solar orbit changes direction continuously as the year progresses, rotating through a full circle. The Sun's galactic orbit points roughly toward a constellation called Cygnus. The solar system's CMB motion points toward a region near the constellations Leo and Crater. 4 separate velocities, pointing in 4 different directions, all present simultaneously. Adding speeds that point in different directions requires vector mathematics, combining not just magnitude but direction, resolving each into its geometric components, and calculating the result as a combined arrow through space. The consequence is that no simple addition works. Depending on the alignment of these motions at any given moment, they may partially amplify or partially cancel each other. What this means for Earth's actual CMB velocity is something most people never consider. It changes, not from year to year, not from month to month, from hour to hour. Earth's rotation adds its own contribution, boosting the CMB velocity when the rotating surface sweeps in the direction of the CMB motion, and subtracting from it 12 hours later when it sweeps the other way. Earth's solar orbit adds a seasonal shift. In June, Earth moves in one direction relative to the CMB. In December, it moves in the roughly opposite direction. CMB researchers actually use this predictable annual shift as a precision calibration tool for their instruments, observing the CMB dipole change slightly throughout the year, exactly as the physics predicts. No single number permanently describes Earth's speed relative to the ancient background light. The answer varies with the time of day, the month of the year, and which component of Earth's motion we choose to include. What is pulling the entire local group at 620 kilometers per second? This is where the story takes an unexpected turn. The popular name for the gravitational influence driving this flow, the Great Attractor, has created a widespread misconception. The name implies a single enormous object, a monster of impossible mass pulling everything toward it. But astronomers have found something different. The Great Attractor is not one object. It is a region, a broad concentration of mass in the direction of the Centaurus and Norma constellations, approximately 150 to 250 million light-years away. For decades, studying it directly was nearly impossible for a deeply ironic reason. It lies almost directly behind the densest part of the Milky Way from our perspective. Astronomers call this band of obscured sky the zone of avoidance, a curtain of our own galaxy's stars, gas and dust that blocks optical light from reaching anything behind it. The gravitational force that dominates our cosmic neighborhood was hidden behind the very galaxy we live inside. Using X-ray surveys, radio observations and infrared light that penetrates dust more effectively than visible wavelengths, researchers gradually mapped the structure beyond. What they found was not one monster, but a vast web. Our local group is part of a larger supercluster, a cosmic watershed of gravitationally connected galaxy clusters called Laniakea, identified in its full extent in 2014 by a team led by R. Brent Tully at the University of Hawaii. Laniakea spans roughly 500 million light-years and contains the mass of roughly 100 million billion suns. Beyond Laniakea, drawing everything further still, lies the Shapley concentration, an enormous aggregation of galaxy clusters approximately 650 million light-years away, representing one of the densest known concentrations of matter in the observable universe. And the flow is not driven by gravitational attraction alone. Cosmologists have established that enormous underdense regions, cosmic voids where matter is sparse, exert a kind of effective pressure, pushing surrounding matter outward. The bulk flows that carry our local group through space are the combined result of both effects: gravity pulling toward dense regions and voids effectively repelling from the other side. Cosmologists have a specific word for all this motion: peculiar velocity. Peculiar here does not mean strange, though the speeds certainly are. In cosmology, peculiar velocity means the motion of an object relative to the general expansion of the universe. The universe is expanding everywhere, carrying distant galaxies apart from one another, the way dots on a balloon separate as it inflates. Peculiar velocity is the additional motion that gravity produces on top of that expansion. It is the motion that reveals the distribution of mass across the cosmos. And the CMB frame, the reference frame in which the ancient background light appears equally bright and equally warm in all directions, is the closest thing physics has to a universal reference point, the closest thing to a cosmic baseline. If everything in the observable universe were perfectly still relative to one another, the CMB dipole would vanish entirely. The existence of a dipole is simply the universe showing us our own motion through that baseline, but it is not an absolute rest frame. In Einstein's relativity, no such thing can exist. No vantage point in the universe is privileged above all others. The CMB frame is special only in the sense that it corresponds to the large-scale distribution of matter across observable space. From your own perspective right now, you are not moving at all. From the perspective of a CMB photon passing through this room, you are hurtling at nearly 1 million miles per hour. From the perspective of the local group's bulk motion, the number grows beyond 1.3 million. Both perspectives are equally valid descriptions of the same physical reality. The honest range of answers to the simple question, how fast is Earth moving, spans from 0, relative to itself, to 825,000 miles per hour, relative to the ancient light of the early universe, to over 1.3 million miles per hour if we account for the local group's bulk flow. No single number is the correct number. All of them are correct. The question contains a hidden trap. It assumes a fixed reference exists. The universe does not provide one. We have now mapped every major layer of Earth's motion: rotation, solar orbit, galactic journey, the CMB frame velocity of a solar system, and a local group streaming through the universe's oldest light. The layers are real, they are verified, and they are enormous, and you have felt none of them. Not a tremor of rotation, not a whisper of the orbit, not a hair's breadth of the galactic race, or the million-mile-per-hour flow toward Laniakea's gravitational heart. The silence is so complete, it is almost suspicious. Why? The answer cannot simply be that everything moves together, though that is part of it. The true answer reaches deeper into the nature of gravity itself, into what it means for a body to experience a force at all, and into one of the most beautiful ideas Albert Einstein ever set down. That answer is stranger, and in some ways more comforting than anything the speeds themselves suggest. The silence is not a coincidence. More than 1 million miles per hour through the oldest light in the observable universe, 500,000 miles per hour through the Milky Way, 66,600 miles per hour around the Sun, 1,040 miles per hour from the spin of the planet, 4 layers of extraordinary speed, each pointing in a different direction, compounding continuously, silently, relentlessly, and the body registers none of them. Not a tremor, not a whisper, not the faintest physical trace. The silence is so perfect it begins to feel like an explanation in itself, but it is not. Something deeper is happening, and understanding it changes what these speeds actually mean. The first thing to understand clearly is what a body can and cannot feel, because human beings are not speedometers. You do not feel velocity. No nervous system in nature detects pure speed. What nervous systems detect, what every inner ear, every pressure receptor, every muscle fiber is designed to register, is force, the push, the press, the resistance of one surface against another, the pull of gravity, the tug of acceleration when something changes the speed or direction of your motion. Forces, not speeds. When a commercial aircraft holds its altitude and cruises at 900 kilometers per hour, 560 miles per hour, the passengers feel nothing. The coffee sits level in the cup. A pen resting on an armrest does not roll toward the back of the plane. If you spill water during smooth cruising, it falls straight down to the floor, exactly as it would in a kitchen. Not toward the tail, not toward the nose, straight down. Because the water, the pen, the coffee, and every passenger are all moving at precisely the same 900 kilometers per hour as the aircraft around them. Their relative velocity to each other is 0, and 0 relative velocity between neighboring objects produces 0 force between them. This is the key. Relative motion, the difference in velocity between you and the things immediately around you, is what determines your physical experience. Your body has no instrument for measuring absolute speed through space, only differences, only the force that arises when your motion diverges from the motion of something nearby. And this is why the scales feel invisible. Everything near you, the air, the walls, the floor, the ground far below, shares Earth's rotation, Earth's orbit, Earth's galactic journey, and Earth's CMB frame velocity. Not approximately, exactly, down to a precision that would embarrass most laboratory instruments. Your velocity relative to the ground beneath you is essentially 0, and 0 produces silence. But silence is not the full story, because not everything in this situation is truly motionless. And here is where the physics becomes genuinely strange. Your body does not feel constant velocity, but your body can detect acceleration. Acceleration is any change in speed or direction, and there are three distinct kinds, each producing different physical effects. The first is linear acceleration, speeding up or slowing down in a straight line. That is the force pressing you into your seat during takeoff, the jolt when a car accelerates from a red light, the deceleration when brakes engage. Each of these changes the speed of your body while the rest of the world does not change at the same rate, and the resulting force is real and unmistakable. The second is rotational acceleration, changing direction while at speed, the turn of a car on a motorway curve, the banking of a plane, the feeling of being pressed outward during a tight corner. Even if speed stays constant, a change in direction requires a continuous force to maintain the curved path. That force is felt. The third is the most counterintuitive: orbital motion, the motion of Earth around the Sun, or the Moon around Earth, or an astronaut inside a spacecraft circling the planet, involves continuous acceleration. The direction of motion changes constantly. The path curves without stopping. By the strict definition of physics, an orbiting object is accelerating at every moment toward the center of its orbit without pause. And yet, the International Space Station orbits Earth at approximately 28,000 kilometers per hour, about 17,500 miles per hour. That is fast enough to circle the entire planet every 90 minutes. The crew experience 16 sunrises and sunsets every 24 hours. And inside the station, they float. Coffee does not fall into cups. It drifts in perfect spheres until someone catches it. Tools let go from a hand stay exactly where they were left. The astronauts themselves push off a wall with one finger and glide the full length of the module without touching anything. Imagine floating inside that station. You would feel no weight pressing your body against any surface, no sense of falling, no force in any direction from the station's motion, just a quiet, complete absence of any bodily pressure, while outside the windows, the entire Earth sweeps below you every 90 minutes at a speed no aircraft has ever approached. How is this possible? The answer resolves something that confuses most people when they first encounter it. Weightlessness in orbit is not the absence of gravity. At the ISS's altitude of roughly 400 kilometers, or 250 miles, Earth's gravitational field still exerts approximately 87% of its sea level strength. Gravity is emphatically present. The astronauts are being pulled toward Earth continuously and powerfully, but so is the spacecraft. The astronaut and the station are falling toward Earth at exactly the same rate. The station falls. The astronaut falls. Every object inside the station falls. All of them fall together, curving through the same orbital path, pulled identically by the same gravitational field. Because nothing inside the station is falling at a different rate than the station itself, no surface presses against any other surface. No force acts between them. The result is the experience of weightlessness, not because gravity is gone, but because everything is falling through it in perfect unison. Earth is doing the same thing around the Sun, continuously falling, continuously missing, and everything on Earth, every ocean, every mountain, every person, falls with it at the same rate. No force arises between you and the ground because of orbital motion. The orbit is shared too completely for any difference to emerge. So how large are these orbital accelerations actually? And why don't they register? Earth's rotation at the equator produces a centripetal acceleration, the gentle outward nudge of the spin, of approximately 0.034 meters per second squared. Earth's surface gravity pulls inward at 9.8 meters per second squared. The rotational effect is roughly 1/3 of 1% of gravity. Real, measurable, invisible to the body. Earth's orbital acceleration, the continuous change of direction as we curve around the Sun, amounts to approximately 0.006 meters per second squared, about 0.06% of Earth's surface gravity. The Sun's galactic orbital acceleration, the barely perceptible curve of our path around the Milky Way, is roughly 2/10 of a meter per second squared. So small that if you place the most sensitive accelerometer ever built at the equator of Earth, pointed in the right direction, and waited for decades, the galactic signal would be lost entirely inside other vibrations. Rotational, orbital, galactic, each real, each verified, each pointing in a different direction, each completely and permanently below the threshold of human sensation. And there is something even more fundamental at work, something that reaches into the very geometry of motion through curved space. Over sufficiently short distances and sufficiently short timescales, any curved path appears straight. Think of standing on a beach and looking at the horizon. The ocean seems perfectly flat. The curvature of the Earth is real, but over the stretch visible from the shore, the deviation from flatness is smaller than the waves. The curve exists, but locally it is indistinguishable from a straight line. Earth's orbital curve bends inward by only about 3 millimeters, less than the width of a pencil, for every second traveled. A body inside a freely falling system over any reasonably short region of space and time cannot detect the curvature of its path using mechanical instruments alone. Albert Einstein grasped something profound about this in 1907, 8 years before he completed the general theory of relativity. He called it the happiest thought of his life. The insight was this: a person falling freely. In an elevator whose cable is snapped, or floating in orbit, or in any laboratory that is freely falling under gravity, cannot distinguish their situation from being at rest in a region with no gravity at all, as long as they stay inside the laboratory and perform only local mechanical experiments. Drop a ball in a freely falling elevator. It does not fall toward the floor. It floats, exactly as it would in the emptiness of deep space, far from any gravitational source. From inside the falling laboratory, the gravity that caused the fall has, in a precise physical sense, disappeared. This equivalence between free fall and the absence of gravity is not an approximation, not a trick of perspective. Within any sufficiently small region of space-time, it is exact. Earth orbits the Sun in continuous free fall. Every structure on Earth's surface, every building, every ocean, every living thing, is inside the same freely falling laboratory. And inside a freely falling laboratory that is locally indistinguishable from a gravity-free environment, constant velocity produces nothing. No force, no sensation. So the body feels nothing because all forces are shared. The accelerations involved are minuscule compared to surface gravity, and the orbital motion is, locally, equivalent to floating freely with no force acting at all. That explains the silence, but it does not mean space is completely passive. On the ground, moving through air produces wind. The faster the motion, the more the air molecules pile up against the moving surface, creating drag, sound, pressure. Supersonic flight tears the air with a shockwave you can hear for miles. This is what motion through a dense medium feels like. Space offers none of that, but not because it is perfectly empty, because it is nearly empty, and the things that do exist in it behave very differently from the dense air of an atmosphere. Between Earth and the other planets, the solar wind fills the inner solar system with a thin stream of charged particles, mostly protons and electrons, blown outward from the Sun at roughly 400 to 800 kilometers per second, or a blistering 900,000 to nearly 2 million miles per hour. This plasma is extraordinarily sparse. The density near Earth amounts to roughly 5 to 10 particles per cubic centimeter, barely anything at all. Earth's atmosphere at sea level contains approximately 27 quintillion molecules per cubic centimeter. Space is not empty, but it is so close to empty that the difference would be invisible to any laboratory measuring technique humans used before the 20th century. The sun's influence carves out a vast bubble in the surrounding interstellar medium, a region called the heliosphere. The heliosphere is the territory dominated by the solar wind, a plasma-filled sphere extending roughly 100 astronomical units from the sun in every direction. 1 astronomical unit is the Earth-Sun distance, roughly 149 million kilometres, or 93 million miles. The edge of the heliosphere, the heliopause, is therefore approximately 15 billion kilometres, or about 9 billion miles, from the Sun. NASA's Voyager 1 spacecraft crossed this boundary in August 2012, becoming the first human-made object to enter interstellar space, and the change in particle density and magnetic field structure was precisely measured as it crossed over. Inside the heliosphere, Earth is relatively shielded, but even relative shielding is not complete protection. Micrometeoroids, particles of dust and rock, often smaller than a grain of sand, travel through the solar system at velocities between 10 and 70 kilometers per second, or 6 to 43 miles per second. At those speeds, even microscopic particles carry enormous kinetic energy. The International Space Station, after decades in orbit, shows the marks of these impacts on its outer shielding: tiny craters, frosted patches on solar panels, small divots in windows that have required replacement. The ISS was designed with layered shielding specifically to absorb particles up to about a centimetre in size. These hazards are real enough to require engineering solutions, real enough to dictate which direction the station orients itself during maneuvers. And then there are the cosmic rays. Cosmic rays are not rays in the familiar sense. They are high energy, charged particles, mostly protons, some heavier atomic nuclei, travelling at extraordinary speeds from outside the solar system. They originate in supernova, in the jets of distant active galaxies, in some of the most violent events the universe produces. They arrive continuously, from every direction, at the speed of light, or very close to it. In 1912, the Austrian physicist Victor Hess strapped radiation measuring instruments called electroscopes to a hydrogen balloon and ascended, alone, to an altitude of approximately 5,200 meters, about 17,000 feet, higher than the summit of Mont Blanc. Every scientist of the era expected radiation to decrease as the balloon climbed higher above the radioactive materials in the Earth's crust. Hess found the opposite. Radiation increased with altitude. His conclusion was precise and radical. The radiation was not coming from below. It was coming from above, from space. Hess was awarded the Nobel Prize in Physics in 1936 for that discovery. When cosmic rays strike Earth's upper atmosphere, at roughly 15 kilometers altitude, they do not reach the surface intact. They collide with atoms in the atmosphere and shatter into cascades of secondary particles: pions, muons, electrons, gamma rays. These cascades spread downward in vast showers, each triggered by a single incoming particle. Most are absorbed by the atmosphere or deflected by Earth's magnetic field before reaching the surface. But some, particularly the muons, do reach the ground. A muon generated by a cosmic ray collision 15 kilometers up can pass through the entire atmosphere and still travel through your body as you read this. Tens of thousands of cosmic ray muons pass through every square meter of Earth's surface every minute. Each passes through you without leaving a detectable trace, but they are there. Astronauts above the atmosphere report flashes of light, visible even with closed eyes, caused by cosmic rays passing through the optic nerve or retina directly. This is the universe making contact with the human body, not through a force that moves you, but through radiation that passes through you. Here is the paradox that all of this builds toward: the silence of cosmic motion, The complete and total absence of sensation from speeds that should feel catastrophic is not evidence that nothing is happening. Cosmic rays arrive. Micrometeoroids leave craters in metal. At high altitudes and in space, radiation exposure becomes a genuine medical concern that constrains how long human beings can remain there. Space is not peaceful. Space is active, and its activity reaches us. But the motion itself, the billion-mile-per-hour flows, the galactic orbit, the solar revolution, produces no force on the body because no force is unshared. Every particle of air, every atom of your body, every molecule of the floor beneath you has been moving at the same speed since this solar system formed. No relative velocity exists between you and your surroundings. No relative velocity means no force. No force means no sensation. The silence is not proof of stillness. The silence is proof of perfect shared momentum, a community of motion so total that nothing inside it can measure the motion itself. And yet, one possibility remains that this entire framework does not address. Everything we have described, rotation, orbital motion, galactic travel, CMB frame velocity, involves motion through space, objects moving within a pre-existing backdrop. But the expansion of the universe is something fundamentally different. Galaxies are not moving through space away from each other. The space between them is growing. The distance increases not because the galaxies are flying apart, but because the medium they sit inside is itself stretching. If that is true, if space itself can expand, then the rules governing what a body can and cannot feel may not apply in the same way. An expansion of space might reach into every structure, every atom, in a manner unlike any motion we have discussed. Whether that expansion constitutes a kind of motion, and whether it leaves any physical trace at all on the objects embedded within it, is a question that leads directly into the deepest and most unresolved debate in modern cosmology. The expansion does not work the way any of the motions we have described so far work. Every layer of speed we have mapped, the rotation, the orbit, the galactic journey, the CMB frame velocity, involves objects moving through space, things traveling from one location to another across a fixed backdrop. But the expansion of the universe involves no backdrop, no pre-existing stage that things are moving across. The space between distant galaxies is not something they are crossing. The space between them is growing, every moment, in all directions, without a center, without an edge, without anything for the expansion to be expanding into. An understanding that single distinction changes almost everything that comes after it. The best way to grasp what this means is through an analogy, but an analogy that must be used carefully because it has real limits. Picture dots drawn on the surface of a balloon. When you inflate the balloon, every dot moves away from every other dot. No single dot is at the center of the expansion. From the perspective of any one dot, all the others are moving away. The expansion happens everywhere on the surface simultaneously. This is how the universe expands, not from a single point, not outward in one direction, but uniformly at every location, in every direction at once. But the balloon analogy has limits that matter. The balloon's surface is two-dimensional. The universe is three-dimensional, and possibly more. The balloon expands outward into the air surrounding it, into a pre-existing space. The universe expands into nothing, no surrounding void, no outside. The universe is not expanding into anything, because the space itself is all there is. Every direction you could choose to go is inside it, and the balloon has a center inside it, the air that the universe has no equivalent of. There is no cosmic center toward which the expansion is proceeding. The Hubble-Lemaitre law describes this expansion with precision. The law states that the recession speed of distant galaxies increases in proportion to their distance from us. The constant of proportionality, called h0 for the Hubble constant, describes how fast space is currently expanding per unit of distance. Scientists measure this expansion rate in kilometres per second per megaparsec. A megaparsec is an enormous distance, roughly 3.26 million light-years, a distance so vast that light travelling continuously from the moment of the oldest human cave paintings would cover only a tiny fraction of it. At 1 megaparsec, the expansion carries galaxies apart at h0 kilometres per second. At 2 megaparsecs, twice as fast. At 100 megaparsecs, 100 times as fast. And here is where what seemed like a settled measurement fractures into one of the most serious unsolved disputes in modern cosmology. Two different ways of measuring h0 give two different answers, not slightly different, not within experimental error, genuinely, significantly, irreconcilably different, and no one knows why. The first method measures the early universe. ESA's Planck satellite studied the cosmic microwave background, the ancient light we explored earlier, with extraordinary precision, and extracted a value of 67.4 kilometers per second per megaparsec, plus or minus about half a unit. To put that in plain terms, for every 3.26 million light-years of distance, recession adds about 67 kilometers per second to a galaxy's speed. The second method measures the nearby universe, a program called the SHOES Collaboration, led by Adam Rees of Johns Hopkins University and the Space Telescope Science Institute, used a completely independent chain of measurements, working outward through increasingly distant standard reference points, and arrived at 73 kilometers per second per megaparsec, plus or minus about 1 unit. Both measurements are precise. Both have been repeated, checked, and challenged extensively. Both are currently holding firm, and they disagree by roughly 5.6 units, at a statistical significance of approximately 5 to 6 sigma. In scientific terms, 5 sigma is the threshold at which a result is considered a confirmed discovery rather than a coincidence. A 5 sigma disagreement between two measurements of the same thing is not a rounding error. The scientific community calls this the Hubble tension, and it has become one of the most actively debated problems in all of physics. 3 broad possibilities exist. First, that one or both measurements contain an undetected systematic error, some calibration flaw or unaccounted bias that has so far evaded discovery. Second, that the tension reflects some genuine physical difference between the early and late universe that the standard cosmological model does not account for. Third, and most provocative, that the discrepancy is pointing toward entirely new physics, new dark energy behavior, new interactions, something outside the current framework. As of now, no possibility has been ruled out. The mystery remains wide open, but there is another aspect of cosmic expansion that most people never hear about, one that, when first encountered, seems to flatly violate the most fundamental law in physics. Distant galaxies are receding from us faster than light, not some of them, many of them, and this does not violate Einstein's relativity, because this recession is not motion through space. Space itself is expanding. Relativity prohibits objects from moving faster than light through space. The expansion of space is not that. The fabric itself stretching carries galaxies apart from one another, the way an inflating balloon carries its dots apart, not because the dots are moving, but because the distances between them are growing. There is no local violation. At any given point in space, physics works normally. Nothing passes through anything else at faster than light speed, but the practical consequence is real. Beyond a certain distance, roughly 14 billion light-years from us, the expansion is already carrying galaxies away faster than light. We call the boundary of that region the Hubble sphere. Every galaxy beyond it is currently receding faster than any signal can chase it. Any light they emit today will never reach us. However, And this is the part that surprises most people. The Hubble sphere is not the edge of the observable universe. The observable universe is larger, considerably larger. Its present radius measures approximately 46.5 billion light-years in every direction. That is the distance to the farthest regions from which light has ever had time to reach us, from a universe only 13.8 billion years old. The apparent contradiction resolves when you understand how light travels through expanding space. The most ancient light reaching our telescopes, the cosmic microwave background itself, was emitted when its source was only about 42 million light-years from us, a relatively small distance. Over 13.8 billion years of travel, the universe expanded continuously, stretching the path of that light as it crossed. Meanwhile, the source kept moving outward with the expanding space. By the time its ancient photons finally arrived, their source had moved to a distance of roughly 46 billion light-years. The light reached us. The source did not stop. There is also a third boundary, the most consequential one, called the future event horizon. Objects beyond roughly 16 billion light-years from us are already on a one-way path away from us, receding so fast that no signal they ever emit in the future will ever reach us, even with infinite time. Not a signal emitted today, not a signal emitted 1 trillion years from now. Gone permanently, not because they cease to exist, but because the expanding space between us will stretch every signal they send until it never arrives. And yet, none of this would carry the weight it does without the extraordinary discovery that completed the picture. For most of the 20th century, scientists assumed the universe's expansion was slowing down. Gravity, after all, acts on everything. All the mass in the universe pulls inward. The expansion from the Big Bang should be decelerating, slowly, as the gravitational pull of all that matter worked against it. The only question was whether the expansion would eventually reverse, leading to a big crunch, or continue forever, thinning out into cold silence. By the late 1990s, 2 separate teams were racing to answer that question by measuring Type 1a supernovae in distant galaxies. Type 1a supernovae, the explosion of a white dwarf star that has collected just enough mass to cross a specific physical threshold and detonate, always detonate at almost the same peak, brightness. That consistency makes them reliable distance markers. Measure how bright a distant Type 1a supernova appears, compare it to how bright it should be if we know its true luminosity, and you can calculate its distance. Then measure its redshift to determine how fast it is moving. Plot both across a wide sample, and read off the history of the universe's expansion. In early 1998, Adam Rees was running the analysis for one of those teams. The data was in. The results should have shown deceleration, a slight dimming of recession speeds, as gravity gradually won back ground. Instead, the supernovae were dimmer than they should have been. Not brighter, dimmer, farther away than expected. The universe's expansion had not been slowing. According to the data, it had been speeding up. Both teams, Rees and Brian Schmidt's group, and Saul Perlmutter's independent supernova cosmology project, arrived at the same result independently. The universe's expansion is accelerating. Something is pushing it outward with increasing force, growing stronger as the universe ages. Both teams published in 1998 and 1999. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery. The cause of this acceleration carries the name dark energy, not because it glows dark, but because it is invisible, undetected by any direct instrument, and understood only through its effect on the expansion of space. Dark energy accounts for approximately 68% of the total energy content of the observable universe. Everything else, all the ordinary matter, all the dark matter, all the stars and galaxies and gas, makes up the remaining 32%. The dominant component of the universe is something we cannot identify. The simplest mathematical model that fits the data is called the cosmological constant, a fixed energy density of empty space. The idea is that empty space itself carries a constant energy, the same at every point in the universe, pushing expansion forward. Einstein introduced a cosmological constant in 1917 for different reasons, abandoned it after Hubble discovered the expansion, and the constant was reintroduced after the supernova discovery. The cosmological constant currently fits the data, but here is the problem, and this is one of the most disturbing facts in all of modern science. Quantum field theory, the most precisely tested theory in all of physics, predicts that empty space should have a vacuum energy. Physicists can calculate what it should be. When they do, they find a number approximately 10 to the power of 120 times larger than what we actually observe. That is a 1 followed by 120 zeros, a number larger than any quantity that appears anywhere else in science. The predicted vacuum energy and the observed cosmological constant disagree by an amount that has no precedent in the history of physics. Either the calculation is profoundly wrong in a way no one understands, or the observation is somehow wrong, or something is cancelling almost all of the vacuum energy, leaving only the tiny remainder that drives the current acceleration through a mechanism no current theory describes. This is known as the cosmological constant problem, and it remains entirely unsolved. Some researchers have suggested that dark energy is not constant, that it evolves over cosmic time, strengthening or weakening as the universe ages. Recent data from the Dark Energy Spectroscopic Instrument, DESI, published in 2024, found tentative hints that dark energy may not be perfectly constant, preferring models in which its behavior changes over time, but that signal stands at roughly 2 to 3 sigma. Intriguing, real enough to follow, not yet strong enough to constitute a confirmed discovery. The cosmological constant, unchanged and unexplained, remains the best single fit to all current observations combined. But now comes the part that is genuinely reassuring and genuinely strange at the same time. The expansion of space does not act on you. It does not pull at your body. It does not pull at the Earth, the solar system, or the Milky Way. None of the structures in our gravitational neighborhood are expanding. And the reason is simple, even though the fact seems paradoxical. Wherever forces stronger than the cosmological constant operate, expansion cannot compete. Gravity holds galaxy clusters together. Gravity holds the solar system together. The electromagnetic force holds molecules and atoms together. The nuclear forces hold atomic nuclei together. Each of these forces is overwhelmingly more powerful than the expansion at the scales where it acts. Expansion only wins in the immense voids between galaxy clusters, the vast emptiness where no other force is present to resist it. There, dark energy slowly pulls things apart, but not here, not on any scale that matters for life, for planets, or for anything bound by gravity or chemistry. You are not being stretched. The Earth is not expanding. The solar system is not drifting. Our galaxy and its neighbours will remain gravitationally bound for billions of years. But the galaxies beyond our local region, the ones not gravitationally connected to us, are already receding, already crossing the distance beyond which no signal will ever travel between us and them. Given enough time, trillions of years from now, every galaxy not gravitationally bound to the Milky Way will recede past our future event horizon. One by one they will vanish, not destroyed, simply unreachable. The light they currently emit will never arrive. The signals they send will never cross the growing void between us. Future astronomers, born inside our gravitationally bound local group long after every other galaxy has retreated beyond contact, will look outward into a universe that appears to contain only their own stars, no other galaxies, no evidence of the vast cosmic structure we can see today. The the CMB will have redshifted into frequencies far beyond detection. The architecture of the cosmos will be invisible, not because it has ended, but because the expansion will have carried it beyond any possible observation. The universe is gradually erasing its own evidence from the perspective of any observer within it. But before that distant silence descends, while we still have access to these extraordinary speeds and structures, the question becomes practical. All of this motion, the orbital speeds, the galactic velocities, the relativistic effects of moving through space at any significant fraction of light speed, these are not just cosmic abstractions. They have measurable consequences on instruments operating right now, on this planet, in orbit above it, and on every mission aimed beyond it. Ignore the motion, and navigation fails. Calculate it correctly, and extraordinary things become possible. The motion is not just something to contemplate, it is something to calculate. Every mission that has ever left Earth depended on engineers understanding, in precise mathematical detail, exactly how this planet moves, how the target moves, and how the two relate at the exact moment of arrival. Get the motion wrong, and the spacecraft misses by millions of kilometers. Ignore the relativistic effects on onboard clocks, and the most widely used navigation technology on Earth drifts by kilometers in hours. The motion we have been describing, invisible, enormous, continuous, has measurable engineering consequences that affect every spacecraft, every satellite, every phone in every pocket. Let's be precise about what planetary navigation actually means. No spacecraft ever travels in a straight line from Earth to another planet. A straight line would require continuous thrust, colossal amounts of fuel, to fight the sun's gravity and maintain a direct path. Instead, spacecraft travel on arcs, carefully calculated ellipses that use the sun's gravity rather than fighting it. Engineers plot a trajectory that begins in Earth's solar orbit and ends in the target planet's solar orbit, with the spacecraft coasting most of the way on the path between them. A journey to Mars, for example, is not aimed at where Mars is when the spacecraft launches. Mars moves. By the time the spacecraft arrives, typically after roughly 7 to 9 months of travel, Mars has moved far from its launch time position. The mission is aimed at where Mars will be when the spacecraft gets there, like a quarterback throwing not to where the receiver stands, but to where the receiver will be when the ball arrives. Equally precise is the timing of the launch. Earth and Mars align favorably for a minimum energy transfer, only approximately once every 26 months. The time it takes for Earth to lap Mars in their respective orbits, and for the geometry to repeat. Miss that window, and the next opportunity is more than 2 years away. Every Mars mission in history has launched within a tight band of days, determined entirely by orbital mechanics. Retrograde motion, the strange phenomenon where Mars or Jupiter appears to reverse course in the night sky for weeks at a time, is simply a byproduct of this orbital geometry. When Earth, moving faster in its inner orbit, overtakes an outer planet, the outer planet appears from Earth's perspective to move backward against the background stars. Not because it reverses, because we are overtaking it, the same way a slower car on a highway appears to slide backward when a faster car passes it. For 2,000 years, astronomers explained this backward motion by proposing elaborate systems of smaller circles, called epicycles, rotating within larger circles, all centered on Earth. Ptolemy's model required dozens of these nested circles to approximate what the planets actually did. The moment Copernicus and then Kepler recognized that the planets, including Earth, orbit the Sun, and that each planet moves at a speed determined by its distance from the Sun, the retrograde motion required no special mechanism at all. The complexity vanished. The universe's behavior had been correct all along, only the reference frame had been wrong. Navigating the solar system is, in principle, a solved problem. The positions and velocities of every planet are known to extraordinary precision. What lies beyond the solar system is a different matter entirely. Proxima Centauri, our nearest stellar neighbour, sits approximately 4.24 light-years from the Sun, the distance light covers in 4 years and 3 months of continuous travel. In kilometres, that is roughly 40 million kilometres, or about 25 trillion miles. At the speed of Voyager 1, the fastest spacecraft currently sailing away from the solar system at approximately 17 kilometres per second, or about 61,000 kilometres per hour, the journey to Proxima would take roughly 75,000 years. That is longer than the entire recorded history of human civilization, multiplied by 10. No current propulsion system changes this by more than an order of magnitude, but one concept under serious research, the light sail approach pursued by the Breakthrough Starshot initiative announced in 2016, proposes accelerating ultra-thin spacecraft chips to approximately 20% of light speed using powerful ground-based lasers. At that velocity, the journey to Proxima Centauri would take roughly 21 years. Still a generation, but a number that humans can hold. Except at 20% of light speed, a new problem enters, one that does not exist at the speeds of current spacecraft. Special relativity becomes important when speeds reach a significant fraction of the speed of light. At 20% of light speed, the effect is small. A clock aboard the spacecraft would run slightly slower than a clock left behind on Earth, by roughly 2%. After a 21-year journey, the crew would arrive approximately 5 months younger than their Earth-based counterparts. Noticeable, but not extreme. But the relationship is not linear. At 90% of light speed, the time dilation factor grows to approximately 2.3. A traveller making a 10-year journey at 90% of light speed would return to find 23 years had passed on Earth. Their friends aged nearly twice as fast. At 99% of light speed, the factor becomes roughly 7. At 99.9%, it approaches 22. The closer to light speed, the more dramatically time stretches apart between the traveller and everyone they left behind. Length contraction accompanies this. From the traveller's reference frame, the distance to the destination physically shrinks, compressed in the direction of travel by the same dilation factor. A traveller at 99% of light speed would measure the distance to Proxima Centauri as not 4.24 light-years, but approximately 0.6 of a light-year. From their perspective, the journey takes only months, not years. Both the dilated time view from Earth and the compressed distance view from the spacecraft produce the same physical outcome at arrival. They are two ways of describing the same relativistic geometry. These effects are not theoretical. They are measured directly every day by the most humble and abundant objects in the upper atmosphere. Cosmic rays, those high-energy particles from deep space, strike the upper atmosphere approximately 15 kilometers above Earth's surface and create particles called muons. Muons are unstable. Their natural lifespan is approximately 2 microseconds, 2 millionths of a second. Even travelling at nearly the speed of light, a muon should cover only about 600 meters before decaying. 15 kilometers is 25 times farther than any muon should travel before it vanishes. And yet muons reach sea level in enormous numbers. Every square meter of Earth's surface is crossed by roughly 10,000 cosmic ray muons each minute. The explanation is relativistic time dilation. From Earth's perspective, the muons are travelling at roughly 99.4% of light speed. At that velocity, the dilation factor is approximately 9. Their apparent lifetime, as measured from the ground, stretches from 2 microseconds to nearly 20, long enough to travel 15 kilometers and reach the surface. The muons' own clocks, from their perspective, still tick through just 2 microseconds, but during those 2 microseconds, the atmosphere rushes up to meet them, compressed by length contraction from 15 kilometers to something closer to 1.6. The mathematics is different from each frame. The result is identical. The muon hits the ground. One more important clarification. because the old language misleads. Objects do not gain mass as they approach light speed. The invariant rest mass, the intrinsic mass of an object measured in its own frame, never changes. What changes is the energy required to keep accelerating. The kinetic energy needed to push a massive object to ever higher fractions of light speed diverges toward infinity as it approaches c. Not because mass grows, but because the relativistic relationship between momentum and energy means each additional increment of velocity requires exponentially more energy than the last. Light speed for any object with mass remains permanently out of reach, not forbidden by a speed limit, but by an energy requirement that becomes infinite before it is reached. Motion also leaves measurable signatures on the light we receive. When a star moves toward us, its light waves are compressed, pushed toward the blue end of the spectrum. When it moves away, they are stretched toward the red. This is the Doppler effect applied to light, the same principle that makes an approaching siren higher pitched and a receding one lower. Astronomers measure these shifts to determine how fast stars are moving, toward or away from us along the line of sight, building three-dimensional velocity maps of stars, galaxies, and distant structures. Without understanding our own motion through the galaxy, these measurements would be systematically wrong, every Doppler shift contaminated by our own unaccounted velocity. There is a second, subtler effect. Motion through space changes the apparent direction of incoming light. When you run through vertical rain, the rain appears to fall at an angle toward you. The faster you run, the more the rain tilts. Light from stars behaves identically. Because Earth moves through space at roughly 30 kilometers per second in its solar orbit, the apparent position of every star in the sky is shifted slightly in the direction of Earth's motion by up to approximately 20 arc seconds, depending on the star's position relative to Earth's direction of travel. In December 1725, the English astronomer James Bradley began a careful series of observations at the observatory of his colleague Samuel Molyneux at Kew, near London. His goal was to detect stellar parallax, the tiny apparent shift in a nearby star's position caused by Earth being on one side of its orbit in January and the opposite side in July. This would provide direct proof that Earth orbited the Sun. He chose Gamma Draconis, a bright star that passed nearly directly overhead in England, which eliminated the distorting effects of atmospheric refraction. He expected the star to shift north in one half of the year and south in the other, the parallax pattern. Instead, the star shifted in a completely unexpected direction, perpendicular to what parallax would predict, and in phase with Earth's direction of motion rather than its position. The pattern repeated precisely over 3 years of careful measurement. Bradley eventually realized the explanation. He was observing stellar aberration, the tilt of incoming starlight due to Earth's own orbital velocity. The star appeared displaced in the direction Earth was heading, the way rain appears to fall toward you when you run. The angle of displacement was exactly the ratio of Earth's orbital speed to the speed of light. This was the first direct observational proof that Earth moves around the Sun, not from a calculation, not from a model, but from the measurable signature of Earth's actual velocity, written into the apparent positions of the stars themselves. Today, ESA's Gaia spacecraft measures stellar positions to within 1 microarc second, roughly a millionth of the displacement Bradley detected. At that precision, aberration is not a correction to check once and set aside. Every single measurement Gaia makes must be corrected for the full relativistic aberration caused by Gaia's own orbital velocity around the Sun, the gravitational bending of light by the Sun and other massive bodies, and the relativistic effects of the Sun's gravitational field on the arriving light. Without these corrections, Gaia's entire stellar catalogue would be systematically wrong by factors far larger than the measurements themselves. But the most immediately personal consequence of all this motion is one most people carry in their pockets. every GPS satellite orbits Earth at roughly 20,000 kilometres, about 12,400 miles, above the surface. At that altitude, two relativistic effects act simultaneously, and they work in opposite directions. The first is special relativistic time dilation. The satellites move at approximately 14,000 kilometers per hour, about 8,700 miles per hour, relative to the ground. A moving clock runs slower. This makes the satellite clocks lose approximately 7 microseconds per day, relative to clocks on the surface. The second is general relativistic time dilation. At 20,000 kilometers altitude, Earth's gravitational field is weaker than at the surface. A clock in weaker gravity runs faster. This makes the satellite clocks gain approximately 45 microseconds per day. The effects do not cancel. One subtracts 7, one adds 45. Net result, the clocks on GPS satellites run fast by approximately 38 microseconds per day. 38 microseconds, an amount so small it is difficult to perceive as significant, but GPS uses timing to calculate positions. The speed of light is approximately 300,000 kilometers per second. 38 microseconds of error accumulates into a position error that grows at roughly 10 kilometers per day. Not adjusted for 2 days. Position off by 20 kilometers. Not adjusted for a week. The error is larger than most cities. The entire system would become useless for navigation in approximately 2 minutes of unmodelled clock drift. Every GPS satellite ever launched has had its clock deliberately set to a slightly different frequency before launch, offset to compensate precisely for these 38 microseconds, so that once in orbit, the combined relativistic effects bring the clock back to the correct rate. Einstein's equations are embedded in the design of the most ordinary navigation device in everyday human use. The speeds are not passive. The motion we carry is not only something to describe, it is something that must be calculated, corrected for, designed around, and accounted for in every instrument aimed at anything beyond the immediate ground. The invisible motion leaves fingerprints on clocks, on star positions, on the apparent direction of light itself, and the engineers who understood those fingerprints made GPS possible, made the Gaia catalogue possible, made every interplanetary mission possible. All of this navigation assumes a universe that will stay relatively stable, planets in predictable orbits, stars roughly where Gaia mapped them, local cosmic structure essentially unchanged over engineering timescales. But the motions we have described are not static. They lead somewhere. The solar system is moving. Our galaxy will eventually encounter another. The sun will age and change. And the question of where all this motion ultimately leads, what becomes of the Earth, the solar system, the Milky Way, on timescales measured in billions of years, is the final question this entire journey has been building toward. All of this motion leads somewhere, not metaphorically, literally. Every velocity we have mapped is a vector, a speed with a direction, and every direction points toward a future. The rotation continues, the orbit continues, the galactic journey continues, and the structures these motions are embedded within are changing, slowly, on timescales that dwarf human civilization, geological history, and the age of complex life on Earth combined. What awaits at the end of this journey is not a settled story. The universe has not finished deciding, and what the best current evidence suggests about where Earth is ultimately heading is stranger, and in some ways more startling, than the speeds themselves. Not every galaxy follows the general expansion we described earlier. Not every object in the universe is carried along by dark energy, receding outward in every direction. Gravity, where it is strong enough, holds structures together against the expansion. Our local group, the cluster of roughly 50 galaxies dominated by the Milky Way and the Andromeda Galaxy, is gravitationally bound. Andromeda is not receding from us. Andromeda is approaching. Andromeda sits approximately 2.5 million light-years from the Milky Way. a distance so vast that the light arriving in our telescopes tonight left that galaxy before our own species existed, before our genus existed, before the earliest stone tools had been made, and yet that ancient travelling light reveals a galaxy unmistakably moving toward us along our line of sight at approximately 110 kilometres per second, about 68 miles per second. Astronomers have known since 1912 that Andromeda is approaching. For most of the following century, the standard prediction, built on simulations of two massive galaxies under each other's gravity, was that the Milky Way and Andromeda were on a collision course, destined to merge into a single larger galaxy roughly 4 to 5 billion years from now. For a generation of astronomers, this was the established future. Two spirals drawing together, eventually dissolving into one enormous elliptical remnant. That certainty has quietly dissolved. In 2025, a team led by Till Sawala at the University of Helsinki published an analysis in Nature Astronomy that fundamentally revised what we think we know about this encounter, using the most precise Gaia and Hubble Space Telescope measurements of Andromeda's motion, combined with detailed modelling of the entire local group, including the Triangulum Galaxy and, critically, the Large Magellanic Cloud. They ran 100,000 separate simulations of the local group's future. The results shattered the conventional narrative. A direct collision between the Milky Way and Andromeda within the next 4 to 5 billion years, the scenario that had been taught as essentially inevitable, turns out to have a probability of roughly 2%. 2%. The Large Magellanic Cloud, whose orbit runs nearly perpendicular to the Milky Way-Andromeda path, exerts a gravitational pull that significantly deflects the trajectory. When all the uncertainties in the positions, motions and masses of the local group's members are properly accounted for, the probability of no merger whatsoever during the next 10 billion years stands at close to 50%. 50%. The collision that was treated as certain is, as of current understanding, essentially a coin flip. The actual outcome may be a close passage in which the two galaxies sweep near each other and continue on, exchanging stars at their outer edges, or a delayed merger billions of years later than predicted, or no merger at all. The data, as of this writing, cannot tell us which, but here is what the data does tell us, regardless of outcome. Even if the two galaxies do eventually merge, even in the scenarios where they do directly collide, individual stars will not crash into each other. The distances between stars are so vast that even in a full galactic merger, the probability of any two stars actually touching is negligibly small. Picture the Milky Way's several hundred billion stars scaled down so that each star is a grapefruit. The neighbouring grapefruit would be 4,000 kilometres away, roughly the distance from New York to LA. In a merger of two such systems, the grapefruits would pass through each other's space almost entirely without contact. The structure and the light would change. The stars themselves would barely notice. What does change during a galactic encounter is the gas. Vast clouds of hydrogen and dust, compressed by the gravitational interaction of the encounter, collapse inward and trigger bursts of new star formation. Merging galaxies light up with the birth of new stars, blazing briefly before the turbulence passes. Whatever the Milky Way's fate, something extraordinary would fill the sky. While the galactic future plays out across billions of years, closer changes have been accumulating since Earth formed. Earth's rotation is slowing, not suddenly, not dramatically by human timescales, but measurably, continuously, and irreversibly over geological time. The culprit is the Moon. The Moon's gravity raises tidal bulges on Earth, the familiar ocean tides, but also smaller solid Earth tides in the crust and mantle. As Earth rotates beneath these tidal bulges, friction transfers a small amount of Earth's rotational energy into the Moon's orbital energy. The result is a dual process. Earth spins slightly slower each century, and the Moon drifts slightly farther away. Precise laser measurements of the Moon's distance, using reflectors left on the lunar surface by Apollo astronauts, confirm the Moon is currently receding at approximately 3.8 centimeters per year, or about 1.5 inches per year, the same distance a human fingernail grows. The fossil record preserves the history of this process. Ancient coral skeletons and tidal sediment layers grow daily in annual rings, the way trees grow rings. Paleontologists studying Devonian-era fossil corals from roughly 400 million years ago found records of approximately 400 daily growth layers per year. Not 365, 400. Earth was spinning faster. Days were shorter. The same 24 hours we track now is itself a snapshot in the long deceleration of our planet. The Moon's own rotation has already reached the end of this same process. The Moon rotates exactly once for every orbit it completes around Earth, which is why we always see the same face of the Moon from the surface. This is not a coincidence. The Moon became tidally locked to Earth long ago. Its rotation slowed by Earth's tidal forces until it matched its orbital period exactly. The far side of the Moon is not in permanent darkness. It receives just as much sunlight as the near side. What it never receives is a direct view of Earth. These are two different things, and the distinction matters. But the most consequential change approaching Earth's livable future has nothing to do with the Moon, or Andromeda, or galactic collisions. The most immediate long-term threat to life on Earth comes from the star that makes life possible. The Sun grows brighter over time. As hydrogen fuses into helium in its core, the core gradually contracts and heats, increasing the Sun's luminosity by approximately 1% every 100 million years. The Sun is currently about 30% more luminous than it was when Earth formed 4.6 billion years ago, and it will continue brightening. In roughly 1 to 1.5 billion years, far sooner than any galactic encounter, the Sun's increased output will likely begin pushing Earth's surface temperature toward a regime incompatible with liquid water. The precise timing depends on climate feedbacks, atmospheric chemistry, and geological processes that are genuinely difficult to model across such timescales, but the direction is clear. Life as we know it on Earth's surface, complex, water-dependent photosynthetic life, faces its most plausible deadline not from asteroid impact, not from galactic collision, but from the steady, patient brightening of the star at the center of our orbit. The Sun itself will survive this brightening. In approximately 5 billion years, after the hydrogen in its core is exhausted, the Sun will begin the transformation into a red giant, expanding outward as its outer layers swell to perhaps 100 to 200 times their current radius. Whether Earth is physically swallowed by this expanding Sun is genuinely uncertain. As the Sun loses mass in its final main sequence phases, Earth's orbit will slowly widen, potentially moving far enough outward to avoid engulfment. Some models suggest Earth survives as a scorched relic in a widened orbit. Others suggest the expanding envelope will reach it. The honest answer, based on current models, is that we do not know. What we do know is that habitability ends far earlier, not with a dramatic final consumption, but with a quiet, incremental warming over hundreds of millions of years that gradually transforms the planet beyond what any complex organism can adapt to. The Sun will expand. The local group will drift in isolation. Andromeda's path remains uncertain. Earth's days will lengthen. The habitability window will close. Each of these futures unfolding not in catastrophe, but in the slow, inexorable progression of physics. Gravity doing what gravity does, nuclear fusion doing what fusion does, time doing what time does. Nothing violent, nothing sudden, just motion and time. Whatever the fate of the Milky Way and Andromeda, merger, passage, or separation, The broader context will become simpler and simpler over cosmic time. Accelerating expansion will continue carrying the galaxy clusters of the wider universe beyond our future event horizon, one by one, until nothing remains accessible to observation except the gravitationally bound remnant of our local group. Future observers, billions of years from now, if any exist, will look outward and see only their local stars. No distant galaxies, no CMB, no evidence of the large-scale structure that cosmologists today use to trace the universe's history. The cosmic microwave background will have redshifted to undetectable wavelengths. The galaxy clusters that prove expansion will have vanished beyond reach. The universe's evidence of its own origin will have been carried away on a tide of dark energy, leaving only the local island of light surrounded by an ever-deepening void. This is not speculation. This is the mathematically straightforward consequence of the expansion rate we have measured, applied forward in time. Future intelligences, if they exist, may have no way to reconstruct the cosmological history that we, living in this remarkably early cosmic era, can still read directly in the sky. We are alive at the moment when the evidence is still here, when the ancient light still reaches us, when the structure of the universe is still legible. And yet, after all of this, all these velocities and trajectories and futures, the central truth that underlies every number we have examined remains unchanged. Every speed we have described is meaningful only relative to something else. Rotation speed relative to Earth's axis, orbital speed relative to the Sun, galactic speed relative to the CMB, local group speed relative to the Hubble flow. Every single measurement required a chosen reference point. Every single answer changed when the reference point changed. Some of those answers ranged from 0, relative to the floor you're resting on, to over 1 million miles per hour, relative to the ancient light of the early universe. None of those answers is the right one. All of them are right. Earth is neither stationary nor moving with one absolute velocity. It is both and neither, depending entirely on what we choose to measure it against. The universe offers no cosmic ground floor from which all motion can be measured. The question, how fast is Earth moving, contains a hidden trap. It assumes such a ground floor exists. It does not. What exists instead is something stranger and, in its own way, more beautiful. Take a moment with what we have covered. You have travelled from the rotation of a single planet to the recession of the last visible galaxies, from Galileo's ship to Einstein's free-falling laboratory, from the oldest light in the universe to the uncertain future of a galaxy that may or may not be approaching ours. You have held in mind speeds that should feel catastrophic and have felt them, through the physics, dissolve into quiet. That is not a small thing to have done. Most people who have ever lived did not have the language for any of it. Right now, you are sitting still. The ground is solid beneath you. The air is calm around you. Nothing presses against your body from any direction. Every sensation confirms that nothing unusual is happening, and every part of that feeling is accurate. Not because you are not moving, you are moving at speeds that defy ordinary comparison, but because everything around you is moving with you. The air, the walls, the ground, the atmosphere, the solar system, the galaxy, all of it is moving together. You are not racing through the universe in isolation. You are embedded in it, carried by it, part of a community of motion so complete, so perfectly shared, that nothing inside it can measure the motion itself. The stillness you feel is not a deception. It is the truest description of your situation. You are not separate from your surroundings, racing past them. You are continuous with them, moving as part of a whole that has been in motion since the first fraction of a second after time began. You are not racing through the universe. You are moving with it. Tonight, as you rest here, The solar system is covering hundreds of kilometers every second through the ancient background light of the cosmos. The galaxy is continuing its vast rotation. Earth is turning quietly through the dark, carrying everything on its surface, every sleeping city, every still ocean, every creature resting on the ground, together, without exception, without a single detectable force to betray the journey. Apparent stillness is not the absence of motion. Apparent stillness is motion shared perfectly with our surroundings. That is what you have been all along, in every moment of your life. A passenger in the deepest sense, not carried despite your own motion, but inseparable from the motion that carries everything. There is something that has been true about you your entire life. Something you never had a word for, never felt, never thought to question. You have never been still, not for a single breath, not for a single heartbeat, not in the deepest sleep of the quietest night you have ever known. In every moment you have lived, every ordinary Tuesday, every childhood afternoon, every night you lay awake wondering about things too large to name, you were moving through the cosmos at speeds that should feel catastrophic, and you felt nothing, because everything around you was moving with you, completely, perfectly, without a single exception. That is not a small thing to carry out of tonight. You are not a stationary creature who occasionally looks up at a moving universe. You are a traveler. You have always been a traveler. The journey was never something you chose or set out toward. It was the condition of your existence, from your very first breath to this exact moment. You just never knew. Thank you for spending tonight finding out, genuinely, if something shifted in the way you see the sky above you. A like and a subscribe are how you let me know. More journeys like this one are coming. Sleep well tonight. You have covered more distance today than you will ever fully know. Good night.